perspective. So percentage bias differential relay having a specific characteristic in terms of that, and you use that for transformer protection. And I told that that is valid for also any other type of element protection, including distribution line, transmission line, reactor. So many other elements are there, which are also being protected by the uh, differential protection. We'll come forward to other two more relays here. So this is the closing class for protection. Hello. Yeah. So this class will be dealing with two relays, directional relay and distance relay. We will first covering the directional relay and then move forward to the distance relay. So similar to the verification of the characteristics of this directional relay, so the purpose as already mentioned earlier also, that we are testing the relay. We are not developing something new concept or so. We are testing the relay. Is it functioning properly as per the data sheet given by the manufacturer or not at a given instant of time? So what we say here, that in this experiment we talk about directional overcurrent relay. We know this overcurrent part, current is high, then it will operate, otherwise not operate. This part can be definite time, this part can be IDMT characteristics or so, or instantaneous also. The directional part, so we talk about here the direction. Okay. What? The direction of fault. The direction of fault. What is the direction of fault and what is its significance? That we like to understand first, and then we'll go to the characteristics and the principle which is being applied for that objective. So this plus this is nothing but an end operation. So if both are being satisfied, then it is a trip, otherwise not trip. But before that, I think we have to understand what is the direction of fault. So what happens? Earlier discussions we are telling that if a substation is supplying to certain load also through a distribution line and so this is a line, and this is the substation we are talking about. I am taking the Thevenin equivalent, so source will come with its impedance, and this is the load side. So what happens? Any fault happens to be there. So we say that the current, a large amount of current will be there because of this loop impedance is much smaller than the normal situation. This current will be detected here by the relay, which is looking to this. This is a radial system. We call it a radial system because the power flow direction is unidirectional here. But that is not the case always. See a situation here. If in a high voltage system like 132 kV, 220 kV, or 400 kV, many such systems, including if you go to our Kharagpur substation outside the DVC substation, 400 kV system, and so then what we'll see that a transmission line can be connected with interconnected, like in India grid, you can say we have a 400 kV loop. This is a 400 kV loop system, ring system. You can call it a ring system. Similarly, 765 kV ring system also. So what will happen that a line in this section, if we say these are different sections, line section in the system, a line section here, we'll see source at this side also and source at this side also. You got my point now. What you like to say? Here it was radial, now it can be this. So power can flow from left to right, also from right to left also, depending upon the need and so. When a fault happens to be there in this line, so current flows from left to right and also current flows from right to left also, because sources are at both the ends. So that leads to a different situation compared to situation 1 here. This is case 2 situation and so. Now what will happen in this case? In this case, the purpose will be that this breaker here and this breaker here this breaker here, both should be open, so that this side should also no more provide fault current, and this side also should no more provide fault current. Thereby, the fault can be isolated from the rest of the system. So this side system and this side system should operate normally without any this. This is a area you consider think about, and this is another area in that sense. So this interconnection has to be lost also during that time. This is a requirement you consider. So the associated relay here and the associated relay here, this is a called forward-looking relay. They have to be activated. Now we are coming to what is the direction of fault here. So what happens that suppose I'll consider that only line section only in an interconnected system. We have different line sections and the loads will be there and so at each bus. Generally, otherwise we don't desire a bus at some point. So load or generation will be there. So suppose you can see that source here, this end is there, and suppose source this end is there. And now let us, we are looking at this bus. Let us say this is A bus, this is B bus, and this is C bus. So looking at this, if you see here, then suppose this is a relay here, and similarly a relay here will be there to take care of the corresponding breaker at those points. Now let us say fault happens to be there at F point. So the job will be that this R1 relay and R2 relay should act. That is what they design. But what happens here? For this fault, current will flow from this to this, and also current will flow from this to this. But similarly, relay here will be there. Let us say this is R3 and this is R4. This is R3 and this is R4. So what we like to say here that this R3 and R4, because this current flowing from this is also same current, you can say that what R1 you can say that and R2 R1 is looking at, same current will be through this R1, R3 and R4 also. So if we think about an overcurrent principle, then all will be observing the same amount of current. And because this is a transmission system and so CT will be also similar order, and therefore all the three relays will operate as they wish. That is not desirable. So only our desirable from the selectivity point of view. From selectivity point of view, that the faulted section should be isolated. If you try to consider trip at this point R3, then what will happen that this load and this load you can say that or this load and this load will also hamper in terms of that. So that is not desirable from this perspective also. To address that, what you say here is that we selectively figure out that in this case R1 and R2 should trip. So this R1 and R2 need to trip. Then what to do? What to do with that? In this case here at this point, at this bus, instead of R4, the R1 should this, because R4 and R1 both will see the same amount of current, fault current IF from A side. So to discriminate that at R1 and R4, that only R1 should trip, not R4, let us say at this point. How to discriminate? This is about that fault direction we talk about. So if you see this perspective, R4 sees fault in this direction and R3 sees in this direction. Now what is the purpose? When they say this is direction means forward direction, because R3 and R4 are meant for this line and R1 and R2 are meant for this line. So that means that at an R1 and R4 point, they will see, even though they will see the same amount of current, they should be able to discriminate whether the fault is in the BC section or in GA section. To discriminate that, at this point, the corresponding R1 and R4 relay should see whether the fault at this bus is to the right or to the left. Now, if you can discriminate that, then if it is a right fault, then R1 will take care. If it is a left fault, R4 should take care. Even if the current is higher than the pickup section. So yeah. So with that requirement, this is about the direction of fault. Fault is, if a fault happens to be here, let us say this is F1 and this is F2. For this F2 fault, R1 should remain silent, R3 and R4 should operate. So we now say that if classification, this is a two-class problem. This is a two-class problem. What? Left or right? We call in our relay terminology forward or reverse. So for R1, what is forward? F1 is forward and F2 is reverse. And for R4, F2 is forward and the F1 is reverse in terms of that. If you remember, you can say that we are talking about how to achieve this is one way looking into that, the CT polarity connections that they were discussing in terms of that also. Okay. Only current will not may not be able to discriminate, so we require voltage signals, and so we'll see that perspective, how to achieve this perspective. So what we say that only overcurrent is not adequate at times, so we need to consider add directional feature, and the direction means it is a fault direction perspective. We have to add. So what we'll do that current is higher, then the pickup setting, then the pickup setting. Current is higher than the pickup setting, and the direction is forward. R1C is forward. Then we can say that the relay should trip. Otherwise, it should not trip. And that's the reason I told about. You can say that if you can direction part and the overcurrent part, you can make an end operation of both, and both are being satisfied, you trip. Otherwise, remain silent. Otherwise, remain silent or no trip decision. Now, with this idea on this, what is direction of fault and how that is useful in line protection in an interconnected system, not radial, interconnected system, that we see. And in today's application, we see we have a lot of renewable resources. So in a distribution system also, at any point you talk about a solar panel, you can say that with inverter connection, and so inject here also. So if this is substation, a transformer here, so equivalent Thevenin's comes here. So for a fault here, the path of current will be this, and also now the presence of PV also, this will be this. So earlier, what the corresponding earlier system was there without PV, or night time PV will not be there. So it was a radial power flow. Now power flow, you can say that maybe both the way. So therefore current will be only both the way. So both the sources must be isolated. So you require a breakers at both the ends, and also overcurrent relay with, you can say that the directional features also we need in this case. So the protection philosophy, the protection strategy has to be different now in the scenario of these renewable integrations, more and more numbers in the distribution system also, or even in transmission system also. So the objective here in this case is that verification of directional overcurrent relay characteristics. Direction can be known. So, but what happens that someone will put a question, why not only directional relay? So the issue is that if you think about the directional relay, so let us say this situation. So power will flow from here to here. So always the corresponding current directions can be this side or current be this side. So we are not talking about that as a fault situation, and that is not the task of the relay to also trip at that moment. So always you can say that suppose the power is flowing from left to right, so this relay will see in the forward direction, and this relay will see in the reverse direction. And if the power flows from here to here, this will see the forward direction, this will see reverse direction. So point is that in this situation, normal situation, then the corresponding current, voltage, or whatever you can say that will be in the forward looking, current will flow in the forward looking direction at one point and reverse in the other side. But that is not a fault situation. So direction information at that time is not necessary for tripping business and so. So when you require, when it is a fault situation, how to know the fault situation? One way is that if the current is high. So this directional overcurrent relay characteristic is to verify. We know the overcurrent relay characteristic is IDMT also. Here also it is IDMT, and so that part is not our focus. Our focus will be on directionality, direction of fault. So we have a, like earlier case, some theory will see, circuit diagram and connection and see, and what are the different settings arrangement for this, and then observation and verification, and as per our requirement, reporting part and so. So this is about again numerical directional overcurrent relay, and then relay is again Schneider MICOM P183 series, agree 138 perspective and so. These are very powerful relays. We can have, this is not the only thing it has, it can have many more things also incorporated in terms of that. So this is 3-phase relay. So used in distribution system, transmission system, for particularly distribution system is being used, but transmission system we use something different, which we'll talk about distance relay after this presentation. So what is that little bit theory on this? We'll have to add this. Let us say this is a 3-phase system, or you can say equivalently for our study purpose, a single-phase system at this moment. Let us say for clarity, you can extend it to the 3-phase system also. We'll go to the 3-phase system afterwards also. So this is an, as I told, directional things required only when the system is interconnected. Sources are at both the ends. Otherwise, in a radial system, you don't require. Now, what will happen here? For this 3-bus system, L, M, N are the 3 buses. For a fault at F1, as already mentioned, the current will flow from here to here, and current will flow from here to here. So absolutely, we require this breaker and this breaker to be tripped, nothing else. That is from selectivity, isolation perspective, and so. Now, as we say that the perspective and so. So in this case, what will happen if we think about this relay at M bus? Let's say M bus relay I am focusing. The current flowing is here like this. So you can connect the city such that the voltage at this point, if you see about this, or even if we think about this voltage also, source side voltage also. So to this voltage, let us say VL also, to this voltage, this current will, what will happen to this current? Let us say the current is nothing but I am talking about this current I at M bus and for the fault at F1. So if this VL is nothing but this VA, let us say in phase A, I'm talking about phase A, this is phase A only. So if this is reference, you can say that voltage for us, for this case, single phase or so, even it is 3-phase fault or so, then the point you can say that to this voltage, what will happen to this current? Because this part is nothing but an impedance, and the impedance is nothing but offered by the line, and line, transmission line, etc. might have started studying in terms of that. So transmission line has certain R and certain X. X comes from the, consider that omega L, the inductance of this line. So for transmission system, this this is X by R ratio is much higher. For distribution system, it may be less. And this X by R ratio leads to, consider that something like for a transmission system, 80 degree, 85 degree, and like that. What? So this X, the corresponding impedance angle for the transmission system is, if it is 85 degree, positive, because R plus Gx. So that's the reason you can say that the corresponding current will be lagging to this voltage. For this case, fault current IMF1 will be lagging to this voltage by an angle of 85 degrees, let us say. And that is what is lagging in terms of that. So the current, this current you can say that, and the voltage, even at this point also, because this is an impedance, you can say that. So at this point also, the corresponding voltage and current relation, they will be the 2 phases, you can say that will be like this. What we see here, that to the voltage, current will leaving this perspective. And this fault, you can say that we call it a forward fault, because this is the corresponding task of, you can say, relay at this point is to treat this one. So it is forward looking relay, we call it, so that the line section is taken care of in terms of that. Now, if you see this situation from this N side also, similarly there, the corresponding voltage and the corresponding current fed from this side also will be similar in nature. Fine. Now, for a fault at F2, now this is F1. For a fault at F2, we are talking about this at this point. You can say that how this corresponding relay will see. So the corresponding relay, you see here this current path becomes this and current path becomes this. So for this relay, R1 relay at this point, if you see same relay, for this relay, the current direction is reversed now. If you see here, the current direction was from here to here, from left to right. Now the current direction is from right to left, from inside to this. So the relay here observes a reverse current as compared to the earlier current, you can say that, which we talk about here. So therefore, the VA, the current will be reversed to what was here considered in terms of that. So what does it mean? This means that to this voltage, which voltage? This voltage, the current is now reversed. If the current voltage reference is taken as reference, same voltage magnitude may be different for the two situations. If we take the reference, then what we see that because the current is reversed, so we are doing a reverse current here, and there is what this current we are talking about right now. And there this region that to this voltage, this current leads now. This current leads now, and here it was lagging current. So what you conclude from this that for this F1 fault and for this F2 fault, F1 fault and F2 fault for the relay R1 is nothing but this is a forward fault and this is a reverse fault. And for this forward fault, the corresponding current lags the voltage, and here it is current leads the voltage, and that is an indicative of the corresponding fault classification we required, whether it's fault is in F1 side or F2 side, or fault is in forward side or the reverse side perspective, and so. So this is what the basic classification task being done on the directional link part of the system, and so. So what you say that earlier the electromagnetic relays, you can say that they were using the torque pin spool, and in the torque pin spool you can say that what we say that the torque, rotating torque, if you see the overcurrent pin spool also a rotating torque was there. So if the torque is in one direction, it is one direction. If the torque is in the reverse direction, it is reverse direction. So in case of forward looking torque, reverse direction, you can say that torque, if the corresponding disc also is not being allowed, and so. Now no more torque business here. So everything you can say that in terms of the computational perspective. So earlier in the first class, I told about how to compute the phasors. So these are all phasors. So phasors has both magnitude and angle. So if you can compute the corresponding voltage phasor and current phasor, then you can get the angle between voltage and current. And if the corresponding current angle is lagging the voltage, then it is some direction of fault. If it is leading, then it is some direction of fault. So that is what a straightforward conclusion we can think about in terms of that. So in this system, as we see, you can say that we see, you can say that even if we see this corresponding waveform here, so for the solid one is for the F1 fault, forward fault, and the dotted line considered is for the F2 fault. So what we say that if we see this part, so for the same, you can say that voltage and current situation, they are, you can say that out of phase, almost out of phase, 180 degree kind of thing. And that's the reflection, you can say that in the earlier discussion. If the corresponding voltage is at this bus is the reference bus, then the lagging current, you can say that, is the forward fault, and the leading current is for the reverse fault. So in conclusion, what will say that if VM, the voltage at the relay bus, at the relay voltage, which is the relay avails, you can say that, at the locally, if this is the reference, so this will be 0 degree. Now we get any current. We don't know, you can say that this side or that side fault. That is the task of the relay. So any current, you can say that during the fault situation, we got it with a certain angle of, you can say that, let us say phi. Certain angle of phi. So if from these two, you can say that if you see here, how do we find out, you can say that whether it is forward fault or reverse fault. That is the two class, you can say that we have to distinguish. So what we say that if the angle of I minus angle of V. So what is angle of I? Angle of I is, let us say, this equals to phi, and angle of V, you can say nothing but the 0. So with respect to this reference, what is the corresponding angle of I? If this becomes phi, if this phi becomes negative, let us say one philosophy can say that. So if this phi becomes negative, as you here see, is negative, then it is a forward fault. And if this phi becomes positive, then it is a reverse fault. Okay? So this is the conclusion, you can say from this perspective, the phasor diagram we clearly see that if the phi, you can say that is the negative value. Which value? Phi value? Angle of I minus angle of V. How will get the angle of I? By computing phasor I. By computing phasor V of any phase, A or B or so, whatever in relevance to the faulted phase, then I can find the corresponding things. I can find the corresponding phi to this. How we arrive this conclusion? We say that in a transmission system or so, let us assume that the fault path only see the transmission line parameters R plus Jx, and X is much higher than X, so therefore the corresponding current will be lagging from this side. And if we see the corresponding fault for F2, the current, you can say that at this point you can say reverse, so therefore that will be the current will be leading for this relay RM, and you can say that the green mark, you can say that put at this point and so. So, if you see this corresponding that we have plotted here for this voltage of this system, for this F1 fault voltage and the corresponding current, and if we compute the phasor and we get the corresponding IA angle minus of V angle for the phase A, and then we see that you can see that during the fault situation the corresponding angle becomes negative. Here this is the zero line, so this is pre-fault business. And there is a phase change observed, you can say that during this time. So that's the point, you can say that, and because this is negative, we say that they can claim it as forward fault. So what to do? Similarly, let me see, you can say, see that about in case of reverse fault, this is F2 is a reverse fault for this relay. So for this case, you can say that we see that this is the voltage, this is the corresponding current, and the corresponding angle of current minus angle of voltage is nothing but positive value. And we see here this positive value, so this is a case of reverse fault. For this relay, this fault is a reverse fault. So the conclusion, what we say, that for such a system, anywhere any relay, if it likes to, you can say that the direction of fault, then what you need essentially is that we need the voltage information, we need the current information, that is that the phasor, and then you can say that you compute the corresponding angle of I, you find the angle of I minus angle of V, whatever phasor at any window. For the same window, you can say that you compute the corresponding voltage phasor and the corresponding current phasor and find the angle between this. This is nothing but your phi, and if this is negative, it is forward direction. If it is positive, it is reverse direction. So this is the rule or principle, you can say that, which the corresponding directionally will follow in terms of that. So in overall, our conclusion that what this directional relay should do is that two things. One, X is the overcurrent relay and Y is the directional relay. X overcurrent, so current is high, and this is about the consider the corresponding directional information. So when the relay should trip, when it is looking at the forward direction. This is we call the forward direction, because this relay job is to take care of this section, not to this section. So that is what the forward looking relay we mentioned in the relay, you can say that engineering and so. So when this, you can say that both are looking for, this is high, current is high, then the threshold, and the corresponding this is in a forward direction, this end operation will go for the trip decision, otherwise it is a block decision or the restraint decision or so. So trip, you can say, is decided by the X and Y person, and end operation is there. This is the about we talk about in terms of that perspective. Now let us coming to, there are more things you can say that I'll come to later on. You can say that this is seems to be simple, but there are more complexity, and so because of higher accuracy level we require in terms of that. So what in terms of the above directional link principle, I said that whenever any three-phase system happens to be there, phase A, phase B, phase C, any phase is having involved with the fault, you take the corresponding VA and the corresponding IA, see the corresponding angle between them, angle of IA minus angle of VA, and then make a judgment that whether it is forward fault or reverse fault. That is what we learn from this. But this is not adequate. We can go further things. I will elaborate after the presentation for the liberty perspective. So this is the setup circuit diagram for this, and this is MICOM P138 and overcurrent directional overcurrent relay. So it makes a judgment whenever the current is high and direction in the forward side. Its input is 220 volt AC DC. You can give range from this. not necessarily 220. So we have a 3-phase supply here, and we have a 3-phase supply here, and I'm telling you, we can say that. So to this relay you can say that makes a trip decision through this and opens the circuit. To the relay, you can say that the current input is there through this, and there is a voltage, you can say that signal from this side also. Okay? So this is a reference phase. This is a current input. The emitter, you can say that reads the current, and you have a voltage input, you can say that through this signal. So what you do here, that we need the angle between voltage and current. That you can say that is the decision making process for this perspective, and we have to for the overcurrent part, the overcurrent relay part, the current should be higher than the pickup setting. So what we do in this lab experiment is that we don't emphasize on this. We say that we inject, you can say that current, the current is always greater than the high pickup. So that part is satisfied. Now we test whether directional function is obeying or not. So what is the characteristic and all these things that we like to verify in terms of that. So what you see here, that we have a good arrangement here, that we have a phase shifter here. So why do we need the phase shifter? This phase shifter you consider to change the angle between voltage and current. So this circuit is nothing but single phase circuit. So you are emulating like a 3-phase circuit. As I said, you can see that the corresponding other phase voltages are not required in case of the single phase to ground fault perspective, and so the arrangement we have this here. You can have the 3-phase supply also, but we are taking from single phase supply and injecting to this one to test the system whether it is for a single phase to ground fault also it is following the characteristic or not. So what happens that once the corresponding relay finds both the forward fault and the corresponding current is high, then it makes a trip decision, and this part you can see that the current injected to this is stopped. That is what the relay functions in terms of that perspective. So am I audible to all of you? Someone should respond. Someone should respond. Am I audible?
Yes, sir, you are audible.
Okay, okay. Now, what happens that this phase shifter is nothing but, for your knowledge, that this is nothing but an induction motor. And what to do that in that induction motor, if you know that we always have, you can say that it is a rotating transformer. It is nothing but a rotating transformer. So if the arrangement is here, that we rotate the corresponding rotor, stator, giving the input to the stator slowly. So the corresponding 3-phase winding in the rotor, you can say that slipping of course. The corresponding 3-phase winding in the rotor makes different position with respect to the stator, you can say that winding, and gives us a phase displacement with respect to this input voltage, and that gives us, you can say that the corresponding voltage to be varying with respect to this reference. Agree? With respect to this reference is from the directly from the grid side, and the grid voltage is being modulated in terms of the phase angle in the output of the phase shifter. So this phase shifter, you can say, gives you the voltage perspective. So this is voltage measurement, and this is the current measurement perspective. So we notice the what is the corresponding. We set the corresponding current. We keep it greater than the pickup setting. So this part is okay, and then we go on changing the voltage. This phase shifter, the corresponding theta or that the theta or that the phi angle which we are talking about in our earlier discussion theoretical perspective. So what we say that is phi, if you go on changing, when the corresponding angle between and voltage is in the forward looking direction, the relay will operate, otherwise the relay will not operate. So what we check is that when the relay is operating and when the relay is not operating based on the corresponding angle between voltage and current. So that is what we like to verify the corresponding directionality part of the arrangement and so on. So in one way, if this is the voltage, that's what this is I'm talking about now, coming to the manufacturer what they have provided. So generally this kind of philosophy is borrowed from the electromagnetic relay earlier versions and so. So this is one way of consider looking even the experiment we are doing on this perspective. So this is about the voltage and this is about the current. So current you consider is being taken, you consider reference in terms of that, but it doesn't matter, you consider to us. So what is being done, that this is forward direction and this is the reverse direction. And what is that? We have a range of this, you can say that, see here, this is the current. So current here, what is that? To this beta, if this voltage, you can say that goes to a beta, you can say that range, up to this it is there. And this, you can say that in this way, you can say it can up to the gamma. With respect to this I, who? The corresponding voltage. And this, you can say, is nothing but your phi. So the phi angle in the forward directions can be like this. So what do you say that to this voltage, this current lagging? So as I told, either I with a minus of V or V angle minus of I. So either you are taking this as a reference or this as a reference. No problem. From here also you can understand. So therefore, if you twist it, you can say that voltage as the reference, then the corresponding current will lag into this one. So this leaves us, you can say that, take area, I can say, in terms of that. So what we like to see here, that when you're forward looking, you can say that perspective, you can say that relay happens to be there. So we say that the corresponding to this voltage and current happens to be like this. There are so many modulating factors. That's why I don't talk about something like 0 to 90 degree or so. The pre-fault current, I pre, the pre-fault current, and the corresponding fault path impedance, and so arcing resistance, and so are there. So therefore, depending on the experience and expertise of the expertise on the system knowledge, the engineer set in terms of different things. So we'll see that on this perspective, I will go for the setting perspective, and on this on directional overcurrent relay, and see. So on the directional, the current part, we have this IDMT characteristic, same equations what we have taken earlier also, if you remember, the IEEE moderately inverse, you can say that K 0.05, alpha 0.02, and this and this. This is what set in the relay, that P134 series. And now we the nominal current, you can say that is 5 ampere CT, that you say pickup setting it, you can say that is 1.5 ampere. So we keep the corresponding current to be greater than 1.5 ampere always, so that overcurrent part is taken care. Now for a given situations, we take this beta to be 135 degree up to that, and then the corresponding gamma to be minus 45. So 135 plus 45 is close to 180 degree. So this is the range. We talk about, declare it as a forward region where the relay should operate. In the reverse direction, the relay should not operate. This in the 0 to 360 degree operation, you can say that this side it not operate. And as I mentioned, you can say that in this case of a reverse fault, the angle of current between voltage and current will be different, and accordingly to be there. So we call, you can say that the phi to be varying between plus minus 180 degree, plus minus 180 degree range in the numerical calculation and so on. So let us see, you can say that two cases we'll see here. You can say that how the corresponding relay respond to this perspective. So what we say that this is a nominal current 5 ampere, pickup is 1.5 ampere. So that it means that this will greater than this, so it will operate always. And the characteristic IDMT characteristic curve is, as I already mentioned, IEEE moderately inverse curve is taken. And for a given setting, B is 135 with a gamma minus. You can change this also, depending upon your wish, and so those are flexible, you can say, things from the setting. So now we see here, this is a nominal current. Nominal current means the CT secondary perspective. So fixed fault current injected, we mentioned here, fixed fault current injected. So this fixed fault current 2.7 ampere, if it greater than 1.5 ampere pickup setting, so it will go for a trip decision for overcurrent principle. Now we'll check the directionality perspective. So what you say is that the angle between voltage and current, you go on changing. What is that angle? 1, 15, 27, 42, this. What is our setting? That this relay should trip if the angle of, you can say that this should be 135 degree to minus 45 degree. Agree? That is what the setting we have done for the forward looking things. So the corresponding relay will trip, that is directionality is being satisfied in the forward side if the corresponding angle ranges from 135 to minus 45. We'll check that. So what is that? This is the angle part. 1 degree, 15 degree, 27 degree, everywhere it is tripping. 42 also tripping, 64 also tripping, 99 also tripping, 117 tripping, 138 no trip, 134 trip. So this is the transition. This is the transition. So this transition we observe here. Please see here 135 minus 6. So you see here 135 degree. Beyond that, it should not trip, and beyond this side you can say that also it should not trip. So you see here 135 to 138. It means that the 135 is very close to that. If we have option, you can say that we can fine tune it, and because this is a phase shifting perspective, and so we have a resolution like this. So we got in terms of that. So I believe you can say you understand that 135 degree left of that you can say is no trip. So 135 beyond that 138 is no trip for this trip. So this, it means that this side is in agreement. Now we'll look into the other side, that is minus 45 seat. 148 no trip, 156 no trip. This is the reverse side 178. Now we'll go, you can say that minus 6 trip, minus 18 tripping, minus 28 tripping. This is all by modulating the angle between voltage and current to the phase shifter. Current is referencing in our case also, here in this case also. Minus 39 trip, minus 43 trip, minus 46 no trip. So this is the transition, and this is what the minus 45. So this clearly shows that you can say that we are you can say that correctly, you can say that able to identify this. So it means that the relay is operating in this as per the mentioned things, and so this is a no trip, no trip, no trip. In higher range you can say that the minus angle is not tripping, and so throughout the, you can say that range, if you see till minus 170, and this is plus 170, this is minus 180. So I told you plus minus 180. So this corresponds to a 360 degree complete, all the whole circle of this. So this is what this side we are talking about. So what we say that here in this case 135 this side, and this is 45 this side. So this we allocated for the trip decision. Then we say that from the verification we say that up to this you can say that when we change from the positive angle, we talk about, then we say that this is tripping, this is also tripping, and this side it is not tripping. So this means that you can say that the directional and overcurrent principle both are being satisfied in terms of that perspective, and so similarly another case you can say that we are talking about here. So in this case also we kept the corresponding current to be 2.67 ampere, which is greater than the peak of setting. So overcurrent is being satisfied. Only have to check now. We have modified the corresponding beta value to be 170 now, larger for my application, and the gamma to be now reduced, you can say, from magnitude wise I'm talking about minus 45 to minus 10. So if I see this, you can say that now again similarly 4, 16, I go on increasing the corresponding values, and I see that you can say that trip. So this is all trip, you can say that till 165, and this is no trip when 160. So this is the transition. So what is our setting? 170. So this is justified. And then this is no trip, and when you go to the angle of minus, you can say side, so minus 6 and minus 13. So you see here corresponding conclusion, what we say here is that in this case this is the marker here, transition. So the transition you can say that is being also clearly, you can say that is the minus 10 here. So that is also satisfied. And we plot this, you can say that this is the trip region and this is the block region. In a similar case, you can say that in this case, this is the trip region, this is the block region. This is forward fault, this is reverse fault. Okay? And the other point you can say that this is the set characteristics as per the space mentioned here, and the observed characteristics. Set, observe. So they are close by. So we say that the relay is in good condition, satisfying what is mentioned in the things. So this is the verifications how we conduct in the experiment. So you can find these corresponding things in this YouTube link. Our lectures are on the theoretical part is available in this YouTube also. You can look into these two links, and yes, this is same thing into that. And if you like to study more on this, you can go to the Schneider electric book instead, which is available in the website, in this link also. Okay. So page number 164 will clarify you more on theoretical perspective and so. So then report submission, you can say that as usual, we talk about that there will be data sets will be provided to you about trip and block region of the directional relay based on the given two data sets. Then you have to write the number, plot the actual operating characteristic of the relay based on the setting provided, like we showed about the diagram here. This kind of plotting, agree? Trip or no trip, that region you have to show. And then write on your assessment of meaning, whether it is a comment perspective, write your suggestions, perfect comment perspective, whether the directional will operate or not for the following fault cases. You can say that, yeah, so this is a problem given to you on this perspective. So we say here the voltage and current data during fault. These are the settings provided to you, and the pickup current is 0.3 kiloampere. So you have to see that whether the current is greater than this, so overcurrent is happening or not, and then you have to check the angle phi, and the angle phi depend upon that whether the angle is positive, negative, and so, and within this range or not. If it is within this range, it will trip. If it is not within this range, it will not trip. So for these two cases, you can say that whether the relay will trip or not trip, that we have to make. So check whether the directional relay will operate or not for the following fault cases. Now something more on this before going to the further one assignment on the Simulink block develop and then performance study and so. What do you say that you will study in your power system paper towards the end about the fault analysis. We call it a fault analysis. Agree? This fault analysis, this phase-based approach, you cannot move forward. So it requires a different methodology approach, and that is called considered sequence component-based approach. So what is being done? That the phase quantity is being transferred to a sequence component-based approach. So this is what VA, VB, VC. This is a transformational matrix called T. This matrix can convert the corresponding three things. You can say that zero sequence, positive sequence, negative sequence. 0, positive, and negative. 0, 1, 2. Regenerated like this. And these you can say that are nothing but they are decoupled in this space in terms of that. So this is a positive sequence is a balanced phasors. Negative sequence is also balanced three phase, and zero sequence is a single phase perspective. Combination of these three, what you say, decompose. Combination of these three results in, you can say that your individual phase can be obtained by this. And this is a transformational matrix, you can say that, for that perspective and so. So these zero sequence, positive sequence, negative sequence has a great advantage, even including the directional link perspective. 95% of the present numerical relays use sequence component. I'm telling you, 95% around of the numerical relay available in the world, they use, you can say that, sequence component in general. Because of the advantages, one advantage, significant advantage, that there is no mutuality here. It is a decoupled space, so therefore the principle can be applied, you can say that, very faithfully, nicely, accurately. So what you do is that the relay does that once the voltage phasors or current phasors, this is about the phasors. Agree? We are not talking about magnitude only. These are phasors. Once you have these phasors from this one cycle DFT and so, what you do is that you apply the transformation matrix, where alpha is nothing but 1 with an angle of 120 degree. Then you get the corresponding zero sequence, negative, positive sequence, and the negative sequence. We call terminology like this. The negative sequence means this A2, then C2 is coming, A1, then B1 is coming here because phasors are always anticlockwise rotating. So that is the only point. This is positive sequence, this is negative sequence perspective. And I think that study will be there afterward. So this is about zero. The sequence component can be applied obtained from this matrix. Similarly, you can obtain the corresponding current based sequence component from this perspective and so. So once we have this, then what is being done? That the positive sequence balance frame, you can say that this one is similar to the normal balance situation in our system. Okay? So with that conclusion, what you do is that the phi angle which we are finding out from this angle of I minus angle B, so that we designate as phi 1. This is nothing but 1 for the positive sequence, and that is nothing but the positive sequence current minus negative minus the positive sequence voltage. If you find that angle, That is similar to, you can say that what you talk about for the forward, it is this phi 1 will be a negative angle, and for the positive sequence perspective, and the phi 1 here will be a positive angle. If it is positive, it is reverse pole. If it is negative, it is forward pole. There is a negative sequence component which is very powerful in directional linking, widely used, you can say that, for directionality because of numerous advantages in terms of that. You can see in your simulations also, from the Simulink also, what is the advantage there. So what is being done here is that, unlike the positive sequence perspective, minus V2 and I2 are taken care here. Minus V2 means this is V2, reverse it and then take it. An angle between that is taken as phi 2. So then again it follows in the same things. When it happens to be negative, it is a forward pole. When it happens to be a positive, you can say that it is a reverse pole. Okay? For the positive value, it is a reverse pole. Same rule applies. So in general, you can say that for the negative, you can say that for the forward pole, and positive for the reverse pole. So phi 2 can say that is same as this, but the same rule you can say we can apply. But this in this case only difference is that angle of I2 minus angle of minus of V2, not angle of V2. That is the only difference we apply. This is all derived from this principle, theory, and so. Then what you say that we can have, you can say that a Simulink block from this perspective, and in this Simulink block you can create F1 and F2. The Simulink will be provided to you. You can say that as last time also given to you. We create fault at F1 and F2 with respect to this relay. This is the measurement point for this relay, and this is a forward fault and this is a reverse fault. So for F1 and F2, you can say that you create faults with your fault resistance value in the system given with your last digit of the roll number, the way we did, and then we note down the corresponding voltage and current, and make, you can say that, see that voltage and current measures, and see the decision will be trip or no trip in this perspective and so. So Kuldeep, are you available?
Yes, sir. Yes, sir. I'm available.
Now I think Kuldeep will in the meantime, you can say that will take little time to 2 minutes and explain, you can say that, how to simulate and demonstrate you, so that you will not find problem in terms of that, and then we'll go to the directionality, the distance perspective and so.
Sir,
Okay.
just I need just 1 minute. It is starting that MATLAB model.
Okay. Yeah, no problem. So and this week we'll be creating a PDF file for this submission. So this week task will be 2 PDF files. One PDF file for the directional relay, and the other file for your distance relay perspective and so. So this is having 5 pages, and these are the different report preparation tasks you should do. But always write your roll number at the top and make the PDF file accordingly. Okay. Kuldeep, please. I think my presentation will be stopped. Kuldeep, are you able to? Okay. Kuldeep, are you able to hear me? Yes, Kuldeep, move forward.
Hello.
Yes, Kuldeep, you are audible, you can say that, but it is showing busy or something like that. You have started, no? Kuldeep? Kuldeep, are you able to hear us? Yes, we are able to see the side. Your Simulink block. Kuldeep?
Hello, hello.
Yeah. Now we are audible, and you are able to see the slide also.
Okay. So
okay. Go on.
actually, my system was hanging for some time because of this metal Simulink. So now it's fine. So this is the system that we have made. 3-bus system, B1, B2, and here this is B4. There are 2 sources connected here at B1 and at this B4, and the relay is connected at this B2 point. One utilizes this positive sequence voltage and current, one utilizes negative sequence voltage and current. These are the directional relays, and this is the fault block, and we will turn on the fault at 0.1 second, and fault resistance we have set is 0.2 ohm. Then here this display will give you the status of that forward fault. 1 will indicate a forward fault, 0 will indicate a reverse fault. This is the angle of that current angle, and this is the angle of voltage of this is for negative sequence, and this is the angle of current for positive sequence based directional relay, and this is the angle of this voltage for positive sequence directional relay. So now we have created, we are supposed to connect here at this point, which is in the reverse direction of this relay, and for a reverse fault. So now I am going to run it. The fault will be on at 0.1 second. Hello sir, am I audible? Hello. Hello. Hello sir, am I audible? Hello. Okay, so this is the angle of voltage, and this is the angle of current. Can anybody reply whether I am audible or not?
Yes, Kuldeep, you are audible.
Okay, so we can see here that the current is leading. Current is having an angle of 157.3 and the voltage is 24.82. For a reverse fault, we can see the current is leading the voltage. So now we will connect this fault block here in the forward direction, and see here the status showed 0, means it is a case of reverse fault. For forward fault we will get 1. Okay, so now we will connect this block the forward direction of this relay. So you can see here, in case of a forward fault, this is the voltage angle of the voltage, and this is the angle of the current, and these angles are specified in degree. So here we can see that current is lagging this voltage. This is 25 degree and this is minus 25 degree. So for a forward fault, this current is lagging the voltage. So from this, so there is a table in the like in the report submission guideline. So from these two displays, you have to get, you can get the angle of voltage and current, and you have to note down whether it is a case of forward fault or a reverse fault, and accordingly write your remarks. So you are supposed to create fault here and here in the reverse direction and in the forward direction of different resistances, and you have to note down your observations. So this is all about Simulink model. Anybody has any question regarding this? Hello.
Okay, Kuldeep, they can clarify later on. We'll go for this presentation part.
Okay, sir.
So we can. Am I audible, Kuldeep? And this slide is visible?
Yes, sir. Yes, sir. You are audible. And slide is also visible.
Okay. So, friends, moving forward, this is the part 2 of this the lab. So this is 3B. So in the 3B, you talk about, you can say that in the numerical demonstration or observations or laboratory experiment, we talk about distance relay here. And the other thing we are talking about is verifying zone 1 distance relay make REL 511 ABB make so called ABB now Hitachi company. No? So this ABB make relay like to have two terminology. One is distance relay, and then we are talking about verifying the zone 1 operation and so. Kuldeep, can you switch off your mic? You mute it. Yeah. So I will explain like the directional relay, what is distance relay, and then we'll move forward what is our zone 1 perspective. So we talk about distance. What distance this is? This distance is nothing but electrical distance. We talk about here electrical distance. What is that electrical distance? Impedance. This is impedance. How to get this impedance? Is a function of V and I. Vi. Simply, generally we talk about V divided by O, I and so. But in relay science, it does not happen so always. There is some. It is not simply V by I. This I can be a modified current. V can be a modified voltage and so. Generally, in our perspective, we'll see that the current is not necessarily of the same voltage and same current that of one phase or so. Fine. So with that idea, we say that this impedance is nothing but this. So what is being done? The distance relay takes care about the line protection. So this is, let us say, suppression side. And then we have a relay here, distance relay here. So we had this voltage and current measurement at this point. Let us say fault happens to be at F1 in the forward looking side. So what happens that if you see here, from here to here, the corresponding distance, if the line distance here is here to here is 100 kilometer, let us say the fault happens to be at 75 kilometer. So what will happen that from this V and I, let us say V divided by I, simplistic. So V divided by I, this is the Z. So it is a single phase case, assume. So the corresponding Z here, Z of F I put, Z of F during the fault is nothing but the V during that fault period, V divided by I. V divided by I, because this is the path. So this V here divided by I will nothing but give you the corresponding impedance of the fault point. But this impedance is proportional to the distance of fault x into r plus j of x small x. This is in per kilometer or per meter, whatever it is. Accordingly, x will come out. So this x kilometer is there. So now, sorry, this you can put in not x. You can say suppose x will confuse you. So this will be let us say some a, not A, B, C, M. So this M kilometer away, and this is per kilometer impedance of the line. Which line? R conductor and the corresponding X of the conductor. So this X is nothing but refers to your omega L, where L is nothing but per kilometer inductance. I think we have learned by this time about the inductance matrix and so. So this is the distance we really find. So for any line from the voltage and current, the distance relay can compute the during a fault. Of course, during a fault, the distance relay can compute the corresponding impedance, and this impedance, if it is less than a set value, in this case the target is from A bus to B bus, 100 km. So R plus JX into 100 is this line impedance. This is the line impedance, we call the Z line. So during the fault, the ZF will be smaller than the Z line. That is what our understanding. So this, if this is satisfied, the line, the corresponding relay should take a decision and be open the breaker. And that's the reason this is a very powerful relay for line protection, particularly for transmission systems. So in India, you can say that REIT will find this, you can say that relay being widely used for transmission network protection. So our purpose is next about consider what is zone 1. Agree? What is zone 1? So let me explain something on zone 1, then we'll see that. Suppose what happens, this is a line, there will be subsequent line, and we are looking from substation side. That can be interconnected, that can be so also. So what we see here, this relay here, its objective is to take care of this line section AB. Let's say this is C. So this is the area, a line section, the relays R1 should take care. It computes the fault impedance using the current information and the corresponding voltage information. Current information from CT and voltage information from the PT, potential transformer. Okay? So why require this? Because you have to scale down the corresponding voltage and current to a lower level suitably, so that this becomes substantially low to be compatible to the your relay, digital relay. Agree? So this is voltage and current information. From this current and voltage information, the relay computes the corresponding voltage phasor and the corresponding current phasor and finds the corresponding impedance. So whenever a fault happens to be there, as we know, that this impedance will be smaller than the line impedance and the relay trips. One way is that during the fault situation, the corresponding I, the fault current becomes larger. So V divided by I will be smaller. With that philosophy, we say that we consider the relay will trip. Now, but what happens there, the corresponding current transformer sometimes saturates. There may be current transformer particular in the differential relay also you observe that setting CT ratio may not be proper and so. So also with the problem with the PT also. Now in that case, the corresponding PT potential transformer. This is again that to say that during the transient process, transition from steady state to the fault perspective and so on. So there is one uncertainty. Furthermore, you see here, suppose there will be another relay here, R2, will take care of this BC portion. Now let us say there is a fault here very close to this one. Very close to this one at this point. Now what will happen? The relay at R1 finds the corresponding current to this. But the fault is, you consider this F2 fault is in the section BC. So it is not a jurisdiction. So what will happen here for this F2? This relay will see the current. This relay will also see V divided by I. But because it is very close by, so it will confuse whether it is within the AB section or beyond AB section. Okay? So that's you can say because of the current voltage measurement, uncertainty, computational process, and so many things. There's so many things I'll add. You can say that another thing, like whenever a fault happens to be there, the conductor may touch to the ground or the tree may touch to the conductor and so. Before this touching happens to be there, because of the high voltage, there will be arcing. Okay? There will be arcing. High voltage lab will be exposed to that also. So this arcing consider is nothing but the rupturing of this air because of the high voltage. So some 30 kV per centimeter peak it can sustain, and beyond that it cannot sustain. So this will be a conductive medium, and that path, arcing path, has certain resistance, and again it goes to the path of, you can say that, to the ground, to the system grounding, transformer grounding or so. Okay? So this grounding, you can say that path has a certain impedance. The tower through which it passes also, tower putting resistance happens to be there, and so these are different factors, you can say that, which can also accounts for the arcing resistance, or we call the fault resistance path, and so that will be added to it. So therefore what will happen, even the corresponding fault happens to be here, sometimes you can say the VI will be more than the Z line, and then in that case the relay will see as if the fault is beyond P, and it will remain silent. Then this becomes a detrimental thing. To avoid this, to avoid all these uncertainties, what is intelligently done is that we divide these sections, AB section, into different portions. Like I'll show you. So we'll say, consider this section recipe. So for AB, for this relay, we talk about this is a zone 1. This is zone 1 up to 80%. And then we talk about the zone 2, like something like 120% up to, or 120, 150%. And then start zone 3. This is about the y-axis is time, and there are also reflection options. So up to 80% of the lines we take about this, because this 20%, this portion is an uncertain portion. The relay cannot decide quickly that to say whether the fault is beyond that and that. So what the corresponding relay at R2 does, this relay R2 also similar thing, zone 1 up to 80% of this BC section, and then zone 2, and then zone 3. Okay? Like that. Both have considered similar things. So what will that, for a fault here, this zone will pick up, and the corresponding relay here will trip. For this fault, this relay will be uncertain whether it is internal or external. So what will that? It will wait some time, delay it, 15 cycles, 20 cycles, and so 0.4 second, 0.3 second kind of thing, and delayed you consider, because if this fault seen from here, if this relay is not taking care quickly, instantaneously, then it will wait some time and then trip, like the backup things we talk about in case of overcurrent relay and so. So this is about the zone 2, and zone 3 is further delayed. What happens that in case of this breaker does not open for this fault, problem with this breaker or relay and so, then there must be a backup. So as a backup, you can say that here you have to trip. So this is about zone 3 perspective and so. So with this kind of thing, we have zone 1, 80%, 85% kind of thing. With more accurate today's numerical relay, we can go up to 90% also, depending upon your requirement and so. And then zone 2 and zone 3 and so. So here in this laboratory, we will talk about only zone 1. It takes about this, and this is instantaneous, no delay, quickly, as early as possible. These are delayed thing, further delayed. This is 1 second kind of thing. This is something like 0.4 second or so. That is the philosophy, like the coordination things in the overcurrent also we are talking about that kind of thing. So that's the purpose, that our purpose is verification of zone 1 for the distance relay. So the distance relay is REL 511, quite powerful in terms of that. So let us say have some little bit theory, you can say that concept, that what is, how this distance relay functions, and then we'll proceed in terms of that. So I have already elaborated your background on that. So let us say this is a 3-phase fault in the line, like here. This is x, and this is 1 minus x. X is percentage of distance or per unit distance from the fault from this side to this side, and this side will be 1 max. So total will be 1. So something to think about that. So this x into Z1 Mn, that is x into Z1, and the point sequence impedance Z1L. we call point-sequence impedance. And I told you consider point-sequence voltage current. So now it is point-sequence impedance. That is what the fault analysis reveals. So from there you can say that we see all the settings that I told you about the zone 1 setting up to the 80% is nothing but the point-sequence impedance, not simple impedance. So this is during the balance condition. So this Z1M and this part, you can say that is nothing but the theory says that this can be on this fault, you can say that perspective, analysis perspective, all three phases are the balance situation. So this reveals that any phase for the three-phase fault case, any phase can be voltage and current pair can be often considered to find out the we call the Z apparent. Z equals to V divided by I, and if this is smaller than we consider your Z1 considered setting, where Z1 setting is nothing but your 80%, let us say 0.8 of the Z1, the line. Then we trip, otherwise not trip. So the computation of this we call apparent impedance, or we call scene impedance also. Scene impedance. Then the relay, if the relay sees the impedance to be less than you consider this Z1L, then it trips, otherwise it will not trip. So this is about we are talking about the zone 1 performance of the distance relay perspective. For a line to ground fault, phase to ground fault, this derivation is there. I'm not going to that. So here the corresponding relations from the fundamental, and this is nothing but we call the sequence network, and so if you are not aware of this now, after you can say that during your towards the last and end of this power system course, we'll study fault analysis. In the fault analysis, you can say that we'll knowing all these perspectives. This is PT sequence, this is NT sequence, this is zero sequence diagram, and so. So from this analysis, the apparent impedance or the seen impedance by the relay, because this target of this considered the relay distance relay to get the corresponding positive sequence impedance for zone 1. For zone 1. Don't confuse this one. This is zone 1. So this positive sequence impedance has to be there. So here you see that this happens to be, if the fault happens to be phase A to ground, then the relations should be phase A voltage upon phase A current plus a factor of this, we call zero sequence current. So that's why I was telling that it is not V divided by I like this, not like V divided by I like this. Okay? So the corresponding current is a function of the phase current plus some other current. Now, what is this zero sequence current? If you see, you can say that I0 equals to it is the I ground current divided by 3. I ground current divided by the 3. And the K0 is a factor. It's called the zero sequence impedance of the line, positive sequence impedance of the line, the suppression of this upon the positive sequence impedance of the line. So this is some derivation. So line, these are you can say available from the line data parameters, and so this is known to the engineers, you can say from the system data, and then based on that you can say that they put this corresponding K0 value to the relay, and the relay computes the corresponding Z using what? The voltage information and the corresponding current information. The voltage and the current information. The corresponding current, you can say that I0 is computed from this IA plus IB plus IC. This is nothing but that ground current I am talking about, divided by the 3. And using this zero sequence current and the corresponding phase current in that one, the relay can say that takes the corresponding, computes the corresponding Z apparent. If this Z apparent is less than the corresponding setting, the relay trips, otherwise remains silent. Again, in the context of zone 1. So now let us come to the consider the circuit diagram of the system what we use in the laboratory. So this is the distance relay part, REL 511. So that REL 511 by this ABB, earlier ABB, now it has and so. This part you consider of this part you consider from this to this part. Now what is here, and but this part towards the right you can see about our arrangement in the system. So this is a three-phase supply. This is a supply side, and we have a conductor here. So the relay trips the conductor here whenever there is a fault in the system. What is the system? This is the system side. System side I'm looking to here, and these are, you can say that our transmission line section. If you see here transmission line section, in one page, in another page, and in another page. And this transmission line section is connected to the load. This load in our case is 3 ball loads, simple ball loads. And what are the transmission line? We have 3 coils. I think in the video you can see 3 coils. You can see that coil has a resistance and inductance. So it emulates, you can say that, the corresponding transmission line. Very similar to that. This wound, the inductance is achieved such that you can say that it at 80-85 degree kind of thing we will achieve in terms of that. So the and these parameters of the line are known to us because the inductance and the resistance values are known to us. What to do here? In addition to that, what are the facilities available here? That we have to create fault. Now, how to create fault? You see here, you can say that in our case, the we see here that we have a switch here. If I can expand this, if we have a switch here, and this switch you can say that we can make it ground. We can make it ground in terms of that. So this ground in terms of that, if we see that creates a fault. So what happens that from this side the current flows. This is the source side. Current flows here, and go to the ground. So this side you can say that is the faulted path perspective, and so similarly you can close here. This is if you say this is phase A, this is phase B or phase C, then you can close here, create fault here also. You can create fault here also. But there is this is whole line. This is around 50% of the in the midway. I cannot claim 50%. This is at the midway, you can say, of the line, and this is you can say at the line end. At the end of the line also you can create fault and see. And the line is connected to the load. So we have a scope of creating fault at different points in the system, as I say, made towards the middle in the one or towards the end of the line. So when you are talking about the end of the line in zone 1, for this case it should not trip, no trip, and for this internal, for this one it should trip because this is around 50% of the line. So our business here is that the corresponding distance relay computes the corresponding distance properly or not. Distance means the Z apparent properly or not, and does it trip properly or not, that we'll have to see. So that is the verification task we have. However, the distance relay takes signals from the CTs, and also we have PTs, where you can say that set of 3 PTs, you can say that, which feeds the corresponding voltage. So these are the voltage and current fed to the corresponding distance relay in this case. Now we'll see about the how to verify the performance in terms of that. So the line parameters, as I told, for that transmission line coil model emulating the line, you can say that in terms of that. So we see that the line is having 2 ohm full length, 2 ohm resistance, and 91 millihenry inductance. So there are 3 coils. The line impedance ZL, total impedance becomes equals to, from this above, is nothing but 1.7 with the J 28.59. Highly reactive. Around 28 ohm versus 2 ohm. Agree? So the line impedance happens to be this kind in this kind of thing. So the zone 1 setting of ZL is 80%. So 80% of this we set, and then we got to consider in terms of this. So this is not 2, this is 1.7 ohm. Now then we can say that we get the corresponding 80% of this, 0.8 of this is nothing but 22.9 with an angle of 87 degree. So you see this corresponding angle that earlier in the directional relay also we talked about that. Line has, you can say, that X by ratio high, so that the corresponding impedance angle becomes very high. Now we'll have the verification part. So what to do with that? In the same, you can say that setup, what I told, we'll first monitoring and line impedance verification will do. How I'll do it, I'm telling you, you can say that. So what we'll do is that we know that during normal condition, also the relay provides data. So this is about that screen. Earlier also I have shown, you can see that from this screen you can see the value during continuous process and so. And what the relay does, as I already mentioned, that the relay provides to monitor for monitoring case for normal situation values in this monitor, small in the display units. But whenever a fault happens to be there, it records that event, and through the PC you can get the data and you can analyze them offline for analysis purpose or whatever purpose you say that. What you say that for a given situation, the line to line voltage showing is 421, and the corresponding point sequence current you can see that is showing is 0.340. So line to line voltage is 421, and for a phase to ground fault you can say at the end of the line. For the end of line it will not trip. For zone 1, the fault remains. So during that fault remaining period, because this will not be severe, we notice that the voltage you can say being 421, and the corresponding current sequence current you can say that is 2.87, something like that. Agree? This is normal situation, and this is the fault situation. 421, and this, because the source is very strong, so even the create that fault is not that severe, so that's why voltage is still maintained. And the current here is much higher than the normal current, 0.3 ampere to this. This is nothing but this 0.3 ampere is because of the 100 watt bulb, I think, or something like that. 300 watt bulbs are connected to that one. So now, so this is like a phase B to ground fault. So 3 phases are there: A, B, C. So as already shown in my diagram. So in the diagram I show you, if this is A, this is A, this is B, and this is C. So we created fault here. No, not this, at the line end here, right? Clearly shown here. Now, for that situations, we got this corresponding current by the relay to be and voltage to be this. So as per the theory, and if we apply this, you can say that this apparent impedance calculation. So what you say that 420 by root 3 upon this corresponding current. What current? The corresponding phase current. So phase current computed, you can say that becomes 3 into I1 for a line to ground fault from the data sets. So this you can say that becomes 8.577, and then this is 28.34 perspective and so. So 0.3 versus normal time is nothing but in terms of 0.3 versus normal time current is 0.3, and now you can say that the actual current in the fault you can say that is nothing but from this calculation data available from the relay is 8.577 ampere. So very large current you can say that happens to be there in this case, but still the relay does not trip because our setting is there. So what you set in the relay is in terms of 80% of this. Which one? We have already mentioned our setting is this. This is for the zone 1 setting. So now whether the relay does not trip, so at this point, because we have created at the end of the line, it is observed also that, and now we find this corresponding impedance, apparent impedance calculation using this relations. This comes out to be 28.34. There is a trick here. We see here this K0 value, which that's for the line, is nothing but Z0 minus Z1 upon Z1. But in this case, because the Z1, the point sequence impedance equals to, it is not a line, and so therefore I think it has certain issue in terms of sequence component perspective. So the Z0 value equals to Z1, unlike in a transmission line, Z0 happens to be more than 2.5 times to as high as 6 times also. So Z0 happens to be Z1. So this Z0 minus Z1, this happens to be 0. So K0 factor happens to be 0. So the K0 I0, this factor happens to be 0. So therefore, the apparent impedance in this case will be VB upon IB. So we know the value of VB. VB, you can say that for this is 421 by root 3. And then IB, you can say 8.57. So this gives it 28.34 ohm. But what is our setting? This 28.64, you can say that actual line, the 28.34 ohm, whereas the actual is 28.64. But we know that our setting is 22.91, close to 23. And now the impedance which is being seen by the relay is 28. So this is higher. So Z apparent is higher than the 23, not less. So therefore it is not going for any trip decision. This is no trip situation. So that least we can say that this. So what is the conclusion? We calculated the corresponding line impedance in terms of this, and we found that this is not tripping also, and this is not in zone 1. So zone 1 relay is not tripping for this zone fault. Okay? So therefore we are able to see it here. We are able to measure, you can say that this quantity, and moving forward. Now further we can say that things. This is the beauty of this numerical relay perspective, because you can store the data and see this oscillogram, and so we'll see here how it can be set. So this phase B to ground fault, you can say, created a very close to 60% of the line, because we saw here 22, around 24 ohm as compared to 30 ohm kind of thing. 30 ohm of the total impedance of the line, 28 point something the total impedance of the line, and we said we created a fault here, and the impedance of fault impedance happens to be fault impedance happens to be 60% creation. So now what we see here that this is phase A voltage, this is phase A current, this is phase B voltage, this is phase B current, and this is phase C voltage, and this is phase C current. So we see here you can see that the sinusoidal voltages, three phases. Now you see here the current here is 0, 0, 0. This is normal situation. Now at this point, the marker is straight line you see here. At this point, you see here phase A current still 0, phase B current here. Before this you can see that the phase B current has gone up. No phase C current. So why this phase B current has gone up? Because we have created a fault at this point. So this, and afterwards there is a line tripping. Tripping means no current will flow. So again it becomes 0. Phase A as such was negligible current, phase B again 0, phase C again 0. Do you follow? So that's the reason. So this is the period you can say that up to which you can say the fault was persisting. How do you call this? Switch on the fault in the phase B. So this is the phase B current. So it is a phase B fault. So the conclusion is that high current observed in the phase B, all three zones started, you can say. Now you see here also, these are nothing but the trip circuits. So zone 1 start, and so zone 3 start, and so. So you see here you can say that this is about the normally 0 tripping, no tripping signal, but here this becomes in open. The up, we can say that. So this, if you see this corresponding things to be also zone 1 tripping. So this is also zone 1 tripping. You can say, we can see from here also trip precision perspective, and so. So this is oscillogram, and if you see here, you can see that from this you can show the voltage, current. You can know, you can say, the values are also available to this one from the perspective, and you can conclude that fault has occurred or not, there is trip signal by the relay or not very clearly. So this gives us a scope of further analysis, and so. For the same, you can say that things, we'll now see what are the things you can find from this one. So if you put the cursor here from this to this, so what I already mentioned, you can say same fault, 60% what we say here. Different values are how we can read from this oscillogram is like this. So the first cursor is nothing but your starting point of the fault. So this is offline business. You bring the cursor, and we see here you can say that at this start, and this is the end, and this cursor you can say that is about the tripping signal. At this point, there is a tripping signal issued by this one. How do you decide that? Now we see here you can say that the zone 1 picks up and makes a trip decision. So without any delay, you can say that this will trip. So what will happen that even the relay has given the trip command, this portion to this portion is nothing but the circuit breaker time. The breaker opens, the switch opens, and then finally successfully intervenes the corresponding current. So that's the philosophy in terms of this perspective. And so now what are the things we see here? That on the voltage perspective, we see here this RMS voltage is mentioned here, 0.2442. This is in kV. This is in kV. And then we have a current, you can say that in this case, this current you can say 13.73 or so. So this current mentioned, so voltage and current you get, because this is the faulted phase, agree? So this faulted phase current, the other currents are almost negligible. So voltage by current, you can say that it will give you the corresponding impedance part of this. So what we say here from this perspective, the relay decision time, that is what I say, that 26 millisecond, where up to this, this is the fault inception. This is the relay decision time from the trip signal from this one. So this is 26 millisecond. Relay decision time is 26 millisecond. 26 millisecond in a 50 Hz, you can say that is 20 is 1 cycle. So plus 6 millisecond. So around 1 cycle it took. And then we have this apparent impedance calculation, as I was telling about. This is the corresponding voltage. The RMS voltage is 0.3943, and the corresponding current you can see in terms of this. So 2239 considered voltage, because which voltage will take? The faulted phase voltage, this one, 2393, agree? So 2393 divided by 13.73 the current, so the impedance happens to be 17.42 ohm. Actual impedance up to the fault point is 0.6 into 26.64, because we mentioned, you can say that the impedance of the line, you can say that section is 28.64 into 0.6 is 17 point this. So as compared to this, so this should be 60% fault. We know that, you can say that where we are creating fault. So we know that from the multimeter measurements that what is the impedance. So with respect to that we are comparing. So the relay calculus sees a impedance of 17.42 as compared to this multimeter showing about 17.18 or so. So the apparent impedance here, you can say that is less than the zone 1 setting, because zone 1 setting, you can say that we talk about the 28.64 into 0.8. So this setting, you can say that is higher, you can say, because it is created at 0.6. So therefore the zone 1, this impedance is less than the zone 1 setting, and then it goes for a trip decision, and that is what we observe from this oscillogram also. So now the same diagram I'll show, you can say that as I say. So this is now from the cursor, you can say that this is the relay duration time. From the relay duration time to this cursor till the corresponding zero current, you can say that here. This zero current, relay duration time, this is fault inception time. So this shows 34 per millisecond. So this 34 millisecond, you can say that is nothing but the breaker time. Breaker means the miniature circuit breaker or the vacuum circuit breaker that will be there in the field. So the poles open, and in between the pole, you can say that the arc starts, and then finally the arc is being extinguished in terms of that, and so. So this is about the corresponding things in terms of the breaker opening time. So this oscillogram clearly shows that you can, from here you can know that how much is the relay duration time. Is that relay took long time? No, around 1 second. That is what the zone 1 should trip, because it has to compute the phasors and then make a calculation and then decide, you can say, what is to be done. The other thing is that circuit breaker opening. Your circuit breaker successfully intervene or not, is the circuit breaker correctly functioning or not, because with time the circuit breaker is also not that good, because it is a mechanical device, it will be contaminated, and so and so. So this clearly shows, you can say that different functionality in terms of that. So our remarks, you can say in that perspective, that the zone 1 distance relay trip, you can say that properly for the fault created at 60% of the line, which we know, because this we are talking about verification. And apparent impedance measured by the relay is close to the actual one also, and so we can explain, you can say, for other things also like that. You can watch the YouTube video for these laboratory experiments, and we have distance relay lectures. Some 12 lectures are there, but importantly these are the lectures in relevance to this experiment. You can see from this perspective and so. And on the Snyder book distance module, you can see that also you can read for your more knowledge in this perspective. So on the report summation perspective, so we'll provide you 2 oscillograms today taken in the lab. So 2 oscillograms. So these are 2 cases, agree? So we have to identify the type of fault, which phase is having involved with the fault, phase B to C, phase A to B, phase A to G, or so and so. Wherever you find the current to be high, that is the indicative of that type. Mention the voltage and current, you can say that faulted phase during fault. So you pick up those voltage and current where the fault has occurred, and you find the corresponding V divided by I of that value, like we did in the slide also. So that gives you the corresponding apparent impedance calculation. So Z equals to V upon I, that V and I RMS value, because here it is the K0 value is 0, so that's why you can directly compute from there. Identify whether the corresponding fault in zone 1 or not. From the oscillogram, you can trip signal, you can see that zone 1 has picked up or not. That will say that zone 1 fault or not. If the relay has trip, so this zone 1, you can say that is the setting, what is that? The setting is 0.1 Z line, same, what data given in this case. So this one, same, okay, 0.8 of this is zone 1. If the relay has tripped for the fault, mention the approximate relay duration time, circuit breaker operation time, and so. Agree? So this is what you have to do in this part, and then some remarks and conclusion. So this is 2 cases, 2 pages are to be there. Now there is a calculation here, some CTPT ratio, and so you will understand this. So we put in the page 3 that part. They are simple, so we can understand that part, not a problem. And then we have a Simulink browser, you can see that similar to that, you can see the distance relay performance. In this simulating, you create fault at F1 and F2, and then you can say that you, for this F1 and F2 fault, you can say that you put your fault resistance in the path using your own roll number, last digit, and then find out the corresponding phasors of the phase A. All the faults are phase A to ground. And in this case, you can say that you are using the corresponding relations for the Z apparent calculations this way, where K0 you can say will be there. This will be provided to, you can say that the corresponding line parameters will be provided to you. Now, once you have this phase A and phase A voltage and phase A current and the corresponding zero sequence current in the measurements, it will be available. Then you can find out the corresponding apparent impedance calculation using this relation. And then we say that the corresponding zone 1 tip, you can say decisions you can know, because zone 1 setting will be 80% of the line impedance with that consideration. And then we can say that we can have a comment on this particular. And so this is what the things to be considered. And these are the different, you can create a PDF file to submit this perspective. And so any questions this there? Kuldeep, are you available?
Yes, sir. Yes, sir.
Now Kuldeep will consider that demo, you can see that on the simulating perspective and shoot there. And so okay, I'm just
Sir, I have shared my screen. Is it visible?
yes, nicely. Go ahead.
Okay. So this is the Simulink model that we have developed, and there are three buses B1, B2, B3, and two sources at B1 and B3, and this line is 100 kilometer and this is 60 kilometer line. The relay is installed at bus B1, and here it is taking the reading of voltage and current here. And now this relay will see whether a fault is internal to this internal to the zone setting or external to the setting. Okay, so
No,
so
zone
what
one, zone one.
yes, zone 1. Yes, sir.
Okay.
So it will find whether the fault is in zone 1 or it is outside of zone 1. So as we know, 80% is the zone 1 setting. So this is 60 kilometer and this is a 40 kilometer line. So this fault, when we create a fault here, so it will be inside zone 1, and this is 10 kilometers. So if we create a fault here, this will be outside of zone 1. So when I run, so let me run, I can create a fault here. The switching time is 0.1, means the fault will be applied at 0.1 second, and this is the fault resistance. You can vary the fault resistance here. So now let me run this model for this case. So the relay plots the calculated impedance here. You can see it takes BAI and it plots the impedance seen. Here you can see the impedance came in and fell inside the characteristics. You can see
what is Rx? R is the real part of the Z and X is the imaginary part of the Z.
yes. So for internal fault, we can see the calculated impedance by relay using this B and I measurement fell inside the characteristics, zone 1 characteristics that we have set. So here we can see like what are the x-axis and y-axis also. You can see this is the x-axis, this is the y-axis, this is the zone 1 characteristics that we have drawn by setting 80% of the zone length, 80% of the entire line, and this is the curve of that calculated impedance. And after creating a fault here at 60 kilometer distance, the impedance came and settled within this zone. That means the calculated impedance at the relay is inside the zone boundary. So trip decision will be taken if the if the impedance is within this zone. So let me create another fault outside the zone 1. We can create it like this by connecting it here.
That is F2 we can say in our
the corresponding readings we can get here: VA magnitude, VA angle, I0 zero sequence current magnitude and angle, then zero sequence current compensation factor magnitude and angle, and this is the A phase magnitude and angle. These are the values in serially. Angles are provided in degree, current are in amperes, and voltage in volts. So let me run it. You can see. So this is the kind of curve we see, and you can see this is the zone 1 characteristic, and this red one is the impedance calculated by the relay. And when we created a fault outside the zone 1 of this relay, then the impedance value calculated by the relay settled outside the zone 1. So this is considered as an external fault. So you have to note down, you can calculate this value calculated by the relay using this set of measurements: VA, IA, K0 and I0. So this is what you have to fill up in the table. I am showing you one sample reading.
That is the final settlement point.
Yes, sir.
The settlement point, that settle point you have to put. The
And
starting point is from the load side, so therefore it takes a trajectory like that. The apparent impedance takes a trajectory, so we don't require that trajectory to be there. So the settling point is that final point close to the boundary what you are finishing.
and one more thing, to run this model, there is one file here. We will share two files. One is that this is the main file, and this is multiple xy underscore graph. So to create this graph, this file, this multiple xy graph should be in the same folder as that of this distance, this main Simulink model. Then only it will be created. This will be created. So while running, you should take care of this. So, sir, that's it, sir.
Okay, okay, good. So anybody finds any problem, we can have the query also. So the from our side, both directionally and distantly, things are over. Any questions, anything, any query, is most welcome from all of you. So these are the third 3A and 3B, and the last part is that for the relay lab. Next week onwards, high voltage will be taken care by Professor Kishore. If you have done questions, then you may leave. Thank you. Thank you. We can switch up your screen. Click. Fine. Kuldeep, who is the third one?
Pratik. TA.
Yeah, TA. Who will help us?
Pratik. I think
Yes,
Pratik.
Yes, sir, I am.
Yeah, please, Pratik. Mishra is there? No.
No, sir, Abhishek is not.
Abhishek is not there. No? So
No, sir.
Kuldeep, there is a student forwarded me a mail. I think she approached you that yesterday or so. Today